talking about air traffic delays, and I think I've come from the engineering side of things. I'm an aerospace engineer by training, and I work on aerospace controls. But I also do a lot more optimization, and I have several friends who do OR here. So I think there's two pieces here. The modeling is going to hopefully be of interest to people who are more used to the control side of things, and then the mitigation part is going to be talking about optimization and at-scale optimization. I should also acknowledge my collaborators in this. So the first part of the talk is joint work with my PhD student Hamsa Balakrishnan and Richard Jordan, who was at Lincoln Lab, MIT Lincoln Lab until very recently. And then the second part is with the co-founder of the company, Resilient Ops, Balachandran, on the optimization piece.
Who got his master's here?
Who got his master's here and worked with both Mike and Dave. So goes back to Maryland. I'm preaching to the choir, but I'm going to do this anyway since this is a systems engineering talk. Why we do what we do. And I think it's hard to argue with the statement that air travel has become very much a driver of global travel and commerce. The numbers are pretty large. I think the Airports Council International estimates that in 2014 there were about a little under 7 billion passenger entertainments. So this is somebody getting on board a plane somewhere in the world. In terms of cargo as well, which is considered a little less, there's a lot of cargo, especially in value, that gets transported by air. Not so much the heavy things that we get in terms of by surface, but by value, almost 40% of value of air freight, freight is by air. The thing about demand growing so much is the pain grows as well, and that's going to be a focus of what I'm going to talk about today. So air traffic delays, and Nextor was involved in studies of estimating the impact of this on the US economy. There are a couple of studies which put the estimate annually to be somewhere between $30 and $40 billion, the cost of domestic commercial air traffic delays. There's also an environmental cost to this, so it's about a lot of wasted fuel because of these delays and a lot of additional carbon dioxide that goes in there. What we'd like to do and what there's been a push to do is really modernize the air transportation system, use new technologies in order to alleviate these problems, and that's motivated work both in the US and in Europe. Next generation air transportation systems, they go by next gen in the US or CESAR in Europe, but the idea is that how do we modernize the system to meet increased levels of demand? And really there's, of interest to me are two things that show up here when we think about how the system is going to become. One is there's going to be increased levels of autonomy, and I'll talk a little bit about this later, but we've all been reading a lot about drones in the press. And the second is increased levels of automation, because currently you have human air traffic controllers who are doing making a lot of these decisions and managing the system, but it is clear that you're going to need some sort of automation and decision support to help them do their jobs better. So, motivated by this is just one high-level slide on what I try to do in my work with my students and collaborators. The idea is how do we develop algorithms for air transportation systems that we can go out and actually implement and to make the system better in practice. I think the goals are reasonably easy to state. What I would like to do is increase the efficiency of the system. Of course, what efficiency is, what the right objective is, really depends on who you ask, because what is optimal for a passenger may not be optimal for the airline, which may not be optimal for the system operator, but we'd like to get the system to be more efficient. The second is robustness, because one of the things that we see is right now, we've all experienced the fact that weather in one part of the system can really result in delays everywhere, and we want to increase the robustness of the system and not have cascading delays. And we want to do this while maintaining the incredibly high levels of safety that exist in the current system. Why these objectives are hard to achieve in practice are really threefold. There's probably several more reasons that we can come up with, but for me, there are three main ones. The first is there's a lot of uncertainty, because everything from what exactly the weather is going to be like this afternoon to who is likely to be on, to show up at the airport on time is going to be an issue in terms of the uncertainty. The second is we do have human operators. We have human air traffic controllers, we have human pilots, so there's that human factor element of this. And then the third is that the airlines are ultimately the aircraft operators. They compete with each other. They are, they have their bottom lines and their interests at heart. So we need to find ways to incorporate those challenges as well. What has changed in about the last decade that has enabled us to achieve some of these and make progress towards these is there is now an increasing amount of data. So John joked just before we started that, how do you bring analytics into this, right, into the picture? And I think what we would like to do, our approach is, we'd like to use the availability, the increasing availability of real-world data to build good models. Now, the thing about these models is, we do want these models to be simple and interpretable, because we're going to have to go to the human stakeholders, to the human decision makers, and explain to them what the models are doing. So they can be complicated under the hood, but at a high level, we need sanity checks, and we need to have the ability to convince people that they're doing the right thing, and these are the right models to have, and the right objectives to have. And we want to use this to develop and implement scalable algorithms. And scalable because we know there's going to be an increasing demand, and we want to be able to accommodate that. So ultimately, if we use these, we can build practical algorithms that we can implement, and decision support for human controllers. So nothing that I say today is going to be, I'm going to take the human out of the picture. It's really, let's help them make better decisions by using the kind of algorithmic techniques we come up with. Over the past decade, there's been a lot of work on what are known as cyber-physical systems, including at Maryland. And I think where we're progressing, at least with the air transportation system, is we have the cyber element and the physical element, but it's also equally important for us to take into account the human element when we do the modeling and the algorithm development. So with that sort of broad background, today I'm going to be talking about two problems. The first, as I said, was going to be a more control-flavored, people who come from control systems theory would appreciate it. It's work that we've been doing on trying to model and understand the dynamics of delays in these large networks, aircraft delays. And in particular, I'm going to think about, model this as networks with switching topologies, and I'll talk in detail about what I mean, and try to see how that helps us predict how delays are going to propagate in the system. And the second piece is to try to ease the pain. So once we know how these delays propagate, let's do something about it. And that's going to be how do we mitigate the impacts of delay, and that's going to be a formulation as a large-scale stochastic optimization problem. Okay, so the first lesson here, and everybody probably knows, but let's see how much, is that delays propagate. So one way to see this is I'm going to show a visualization of flight delays in the National Airspace System, NAS for short. Let me set this up. Can you make out the icons in the back?
Can you turn the light down for a second?
Oh, that's perfect. Thank you. Okay. So the aircraft are going to be in gray. We'll start seeing them. Okay. You can kind of make them out, I hope. There are these little gray things that are here. They look a little here on the screen. This is a day when there's weather pretty much only in the Chicago area. In the later part of the day, there was some weather in Dallas as well. Hopefully, in a few minutes, a few seconds, you're going to see aircraft turn yellow. You can see the yellow is clearer. So when aircraft turn yellow, it means that they have more than 15 minutes of delay. And when they turn red, it means that they have more than an hour of delay. So initially, as the day starts, you see that the yellow aircraft and the red aircraft are pretty much around the Chicago area, which is where the weather is. But as it gets, this is around 10 a.m. in the East Coast. By around then, you start seeing that there are flights between Seattle and San Francisco, or Seattle and LA, which now have 15 minutes of delay or even an hour of delay.
About 14 hours in Chicago.
Sorry? Yeah, 14 hours. My record is 8 hours on a plane between DC and here and Boston. So Exactly. But you do see that this delay, and this is the day, let me remind you again, when the weather is entirely out here, right? And you start having delays here. The problem here, of course, is that there is a lot of connectivity in the system, and we'd like to understand the connectivity in the system. There's at least 3 modes in which we can imagine that these delays, these impacts propagate. The most obvious one, and what we tend to see here primarily, is that aircraft connect, right? So the aircraft starts at Chicago in the morning, but goes to Seattle, is an hour delayed getting to Seattle, is therefore delayed by maybe another 45 minutes getting out of Seattle, going to LA, and so on. There's also the crew. The crew connects, the passengers connect. Passenger connectivity is really hard to measure here, and there are very few estimates of this. Crew connectivity is a major challenge for the airlines, to the extent where, as much as possible, when they try to build robustness into the schedules, the airlines will try to keep the crew and the aircraft together, just so that if you're going to infect one node, you might as well only infect one node and not infect one.
In my delay, due to sensible pilot.
That's true. The pilot gets a cold, you're stuck. And I'll come back to the issue of the crew thing. But we're going to mostly focus on what we think are, we believe that most of this is because of aircraft connectivity. Okay, so what we'd like to do is to be able to capture and model these systems. A useful abstraction when we think about this form of connectivity is really to think about it as a network, because that is a natural way of expressing this connectivity. Now, networks are everywhere, right? So networks have pretty much, you name a phenomenon where if something is spreading, networks have been used to model this. So everything from epidemics and rumors to various infrastructure, your energy networks, your communication systems, and so on. There are some things, but what I'm interested in here is what makes air traffic delay networks different, right? Or can we just borrow from network theory that already exists? And there are some assumptions that get made by the majority of literature in network theory, which doesn't really fit into what we're trying to do. So the first is what we mean by a nodal state. So if you think about classical network theory, usually you have, when you think about a node, let's say an airport, or it could be a city, right, where they're thinking, or a subset of the population, they're going to have a small number of states that that node can be in. So for example, if you think about an epidemic model, there are SIR models, which would be that a given node would either be susceptible, which means it's going to be prone to the infection, or it's infected, or it has recovered. Right? So it's a small subset, and this is done for reasons of computational tractability. The second thing, and the same thing holds for links as well, where they assume that two populations or two nodes are either connected or they're not. So it's a binary thing on the link, either exists or it doesn't. The second thing is that they assume that they're unweighted networks, in that, so in fact 0-1 networks, link either exists or not, and they're undirected, which means that there's symmetric interaction. So if I'm connected to you, then you are connected to me, and my influence on you is the same as your influence on me. And then the third aspect of it is that the network structure, this topology, is assumed to be static. And then we can, and I will talk about this as well, things like centrality. What is the most important node in this network becomes a question that we can ask. Now, when I want to model air traffic delay propagation, there are some things which don't satisfy these assumptions. The first is that there is no, even though that the movie I saw showed aircraft icons being either yellow or red, that's really not it, right? So it's not that they have either 15 minutes delay or 1 hour delay. They have any, it's a continuous variable really in that state. Similarly, if I ask for what is the delay going from Boston to Chicago, it is a continuous variable. It's better modeled as a continuous variable. And then the third is they're not symmetric either, which is the delays from Boston to Chicago are not necessarily the same as the delays for flights that are going from Chicago to Boston. So they are asymmetric relationships. And the last point is these are time varying networks, in that the delays from Boston to Chicago at 9 a.m. in the morning are not going to be the same as what they're going to be at noon or what they're going to be at 2 o'clock. So depending on the time of day and the schedules and the demand and everything else and the weather impacts, these relationships keep changing and are asymmetric. Yeah.
So are you going to tell us what the weights mean?
Yes.
And the networks are that varying in the sense that The topology is fixed, but the variables of the node relating to time vary.
Right.
All
So
the
there are
topology
ways.
nodes is same.
So absolutely. So in reality, when I talk about topology and the weights, they can be anything at all, right? So everything is in continuous space, and that's going to just bring us back to I can't do anything with this. So I'm going to try to come up with a computationally tractable way of expressing both the time-varying nature of those things as well as the fact that they're continuous
The
space.
topology is fixed.
No.
No.
You will see that it's not going to be fixed. I'm going to change that. But I'm not going to allow it to be completely arbitrary. Okay, so that's a good question. The question is, what is my network, right, that I'm going to consider here? So for air traffic delays, what I'm going to be doing, and we can have different definitions of this. The one that I'm going to use for the purpose of this talk is that the weight is going to be the delay level. And what we use when we build these networks is going to be the median delay. So at any time, I'm going to look at the median delay of flights that are leaving in this hour between Boston and Chicago. And that's going to be the edge weight for the Boston-Chicago.
Over interval?
Over an hour is what I'm going to take. So these are choices I'm making. So I'm going to take an hour. I'm going to look at Boston to Chicago. I also have a weight on the median level between Chicago and Boston, and that's going to be the weight and so on. So I'm going to have an adjacency matrix that looks like this, which is just what are those weights, those delay levels. This is really going to be a function of time, right? So at any hour, I can find what that matrix looks like.
So the network is monotone because everything is positive.
Yes. And the positive nature of it is going to be important. Everything is non-negative. Yeah. So for example, here, I've just picked up 5 airports. From Chicago to ORD is O'Hare, Chicago O'Hare, to Atlanta, maybe there's 20 minutes delay going out. There is no delay that's coming in from flights that are going from Atlanta to Chicago, but Atlanta to DFW, there's 1 minute going out, but 5 minutes coming in and so on. So I can use this, and anytime you give me the data, I can build the network. Right? Yeah.
So there's no delay, you don't have an arc on your network? Or
Yeah. At this point, I don't, yes. I'm going to have a 0 arc because there's no delay on
so
those
zero arc
flights
means the arc doesn't exist
at that time.
because it's different from having an arc with a weight of 0.
Right, so at this point, at that moment, I'm just going to, so the way I'm going to consider it is when I have my adjacency matrix, I'm going to have a 0 there.
Okay,
And the
so
reason
the
for
arc,
that is at some other time,
okay, because you need to differentiate between airports that actually have flights and airports that don't
right,
have
exactly.
flights.
So the reason I would have a 0 there is
Yes.
because at a different time, I might have a weight there. So that's the reason why I'm going to have a weight of 0 there.
Okay, so those arcs exist, they're just not on that figure.
Right, and,
Okay.
and I think our interpretation is, in this model, there is no delay that's going from here to there at that time. I will talk at the end about extensions. So we're working on looking at multi-layer networks. So when you start thinking about one layer of the network being traffic, then the exact issue that you mentioned becomes important, where I'm trying to correlate traffic flows between these guys to delay flows. And so we do have to consider those differences. But here I'm just going to say there's no delay that ends up going from one to these guys. So once I have that, I'm going to come up with an even more simplified model of the delay dynamics. And it's going to be the following, which is for a state of a particular node, I'm going to be looking at how much delay am I sending out and how much delay is coming in at that particular time. So, and my simplified model is going to look something like this. It's going to say that my inbound delay at airport I at time t plus 1, there are 2 things that happen. One is, because queues build up, there is persistence that happens. Which means that if I was delaying the previous time period, it's not that everything disappears at this moment. So there is some persistence factor that I'm going to call alpha, which tells me how much the inbound delays take. And times whatever my inbound delay was at the previous time, plus the second term, which is saying how much delay is getting pushed to me from all the other airports that I'm connected to that are sending delays out at the previous time. And then similarly, what I can do is for the outbound delay, I say there's some persistence of the outbound delay, plus the delay that I'm sending out, and so those flights are leaving, and so I'm sending out some delay to these other airports.
The IJC are airports.
The I's and J's are airports. exactly, they're nodes. These betas are just parameters. This A is the normalized version of the adjacency matrix, and then this is what the state, the outbound delay state or the inbound delay state at the other airports. So the other way of sort of interpreting the two factors, the two terms that I have is, this is telling me how much delays tend to persist, and this is telling me how much the network effect is. So things that are coming in and going out because of other airports.
What is the interpretation of the betas?
The betas are saying how much of, it's a magnitude for the network effect. And the reason the betas are not necessarily 1 is there is slack that's built into these schedules, right? So just because the flights from the other airport left 10 minutes late doesn't mean that they're going to show up 10 minutes late, because there is some level of slack that's built in the schedule. So you have equal chance of showing up a few minutes early and making up some amount of time. So these betas end up being a little smaller. So I will talk a little bit about the alphas and betas. One of the things is, once we validate these models, we go back and look at those parameters, because they're telling us things about resilience, right? How much delays tend to persist in these systems? How much?
The betas fixed all the time by.
In this, yeah, that's a really good question. So they can be time varying in general. I'm going to assume here that they're fixed, though it doesn't matter, and I'll show you why it doesn't matter to that extent in a few minutes. So what we have from this model is, if I have a state of the system which is just this x bar, which is it's a long vector, right? It's got the outbound delays at every airport at that time, and the inbound delays at every airport at that time. Then if I have a fixed network topology, if you give me a connectivity in terms of delays, then I have this linear relationship on how the system propagates. There's this calligraphic A here, that matrix, which is related to my adjacency matrix for the topology. So it looks like this. And in principle, here these adjacency matrices can be anything, right? So that's really an A with time. In reality, it varies with time. These parameters, let's assume that they don't vary with time. They're sort of airport properties, but this whole thing can do whatever it wants. In terms of modeling, I might be able to build this, but I want something that I can actually analyze and say something about the dynamics. So I'm now going to make an assumption, or rather, I'm going to justify this assumption. But let's suppose we say that the adjacency matrix, it's not that it can be anything at all. I'm going to borrow from what I know from hybrid systems theory and say that maybe it can take a few characteristic values. Right? So it can vary, but it can vary within the set. So then the question becomes, how do I identify that set of characteristic modes? So in other words, what I want to know is, I know that the dynamics, right, varies, depends on the network structure, and I want to identify a few characteristics, a characteristic set of these structures. So then it brings us to a more fundamental question, which is, if I'm given two networks, A1 and A2, how do I tell whether they're similar or different, whether they belong to the same characteristic structure or they're different? And there's two ways that we can think about it in this context. The first is to look at the impact on the dynamics, right? That equation that I said earlier, that I wrote down earlier. And we see that really, it seems to be that the effect of this matrix, the calligraphic A, is of this form, right? So the variation of the state vector x is this beta times A times x bar of t. So which seems to suggest that if I find the principal eigenvector of that this matrix A, then it says that if your delays are in those elements, and you start there, you're just going to stay there. Forms are invariant subspace. So this shouldn't be spectral radius, this should be the principal eigenvector, right? So in other words, the dynamics of this, whether two networks are giving me the same dynamics or different dynamics, can be distinguished in some way by looking at the spectral radius, by the principal eigenvector of this matrix. That's one view. The other view is to say, well, why don't I just look at network theoretic properties? So things like centrality, right? So eigenvector centrality would be a typical way you do it if you had symmetric networks and so on. So we don't have a symmetric network here though, so I can't just look at eigenvector centrality. But Kleinberg, this predates the page rank, right? In the case of web pages, said that if you had directed networks, then there's this notion of hubs and authorities. And the idea is the following, which is there are nodes, every node does some pointing to a bunch of other nodes, and it is also pointed to by a bunch of other nodes. So when I think about the importance of the node or the centrality of that node, there are really two things. How good a pointer, how strong a pointer am I, and how strong is the pointing that occurs to me. Right? So the sort of definition of this is that you're a strong hub if you end up pointing to nodes that are strong authorities. Right? And a strong authority is one that's pointed to by strong hubs. So it's a cyclical thing where I become more important as a hub if the people that I am pointing to are strong authorities. And they become more important because they're pointing to me because I'm more important and so on. So this is just like eigenvector centrality but for directed graphs. Now there's a result from Benzi and others from 2013 which says that to calculate, if I'm giving you a network, a directed network, weighted directed network, and ask you for the hub and authority scores, then that really translates to the principal eigenvector of this matrix. So in other words, it doesn't matter. The hub and authority scores are important because from the point of view of our dynamics, it tells us what the invariant subspace of that dynamics is, but from the point of view of network theory, it's just the hub and authority scores. So what we can do with this is, if I want to identify a set of characteristic network topologies, I can do this by clustering, where what I'm going to use as a feature vector to classify these guys as belonging to, this mode versus this characteristic structure versus a different one is going to be, I'm going to look at the hub and authority scores, but that sort of normalizes the actual magnitude of delays, right? It just tells me what the relative delays at these airports are. I'm also going to look at the values of the inbound and outbound delays. And then the one thing that we don't look at here is whether your delays are increasing or decreasing, so we can add that as well. But these are what we would decide to determine our structure. I know that's a lot, so I'm just going to show you what kind of thing we would get if we actually clustered using these matrices. Okay, before that, so what the bottom line of this is going to be a hybrid system. So if you, this is going to be a system which has a set, the dynamics is going to have discrete modes of operation, but it's going to switch between these discrete modes, and there's going to be a continuous dynamics of the state within each of these modes. These discrete modes are really driven by the topology of the network at that time. So for example, let's suppose I'm initially in a mode where the connectivity looks like this. The system, the delays are going to evolve according to that topology. Right? But then I might switch to a different mode, right? And then I'm going to evolve under the next topology, and then I can switch, and there's going to be that set of dynamics. These switches, because I don't know yet what is triggering these switches, I'm going to assume that these are random switches. So it's going to give me a switch linear system with Markovian transitions. So I'm going to say this.
When you say the network topology time varying, you mean exactly this?
Yeah, I mean exactly this. Which is, it's going to be switching topologies. So, right, exactly. So this is going to be my strong assumption, which is, I said time varying, but time varying in that it's going to be, if I identify, let's say, 10 of these characteristic modes, it's going to be one of those 10 topologies. It's going to randomly switch between those 10 topologies, and I'm going to assume that these transitions are Markovian. So I'm going to end up with a Markov jump linear system. In fact, more stronger, I'm going to end up with a positive Markov jump linear system.
Right.
For this. So that's going to be my model of this.
But I need to have switches at various times. One can argue to what extent you can still do eigenvalue analysis because you have time variation.
Right. So that's a really good point. Which is why I said the eigenvalue analysis that I was doing was assuming that I was in a mode, and the only reason I was doing that, I was using that analysis to distinguish between two modes. Right? Because I agree with you that if otherwise the hybrid system identification problem is intractable, right? If I can switch at any time, then I'm going to overfit that. So I'm going to say there's a small set of things that you can do, right? And I'm going to use clustering and eigenvalue analysis, the eigenvector analysis to identify that small set, and that's all I'm using it for. So this is an example of what we would get. This is based on a year, so 2011 delay data. And what I do here is we cluster based on the hub and authority scores, so the principal eigenvectors of the matrices and the inbound and outbound delays. I get 6 clusters, and then every cluster I look at whether the delays are increasing or decreasing from the previous period, which gives me 6 times 2, 12 clusters. And they look something like this. So I'm going to just read them in order because I think you may not, a few of them, right? So this, for example, is a mode that I call San Francisco increasing. San Francisco, because when I look at this, it looks like the delays are concentrated around San Francisco. This would be San Francisco decreasing because the difference between these two really is, this one is times when the delays were increasing, going upwards. This one was when the delays were going downwards, and they don't look exactly the same. Then you have a mode when, the high mass, right? So system-wide, the delays are high. I should point out that the red lines correspond to a median delay of 45 minutes, right? Which means that I take a median flight between those two airports and it's a 45 minutes.
I understand that you are comparing two graphs.
These are the centroids.
Each has an adjustment symmetry.
Yes.
And you're using the carbon authority characteristic and the metric by which you say something belongs to the same class or not is?
It's okay. The metric, the metric is going to be the Euclidean distance between those vectors, right? So
don't try to do direct phase rank comparison, which you could.
Yes, we could. So here, though, when you give me a new, if you give me a completely, so the clustering uses, this is just medoids, right? So this is just doing Euclidean clustering. And again, when you ask me to classify, if you give me a new network and say, which is the closest network to this, I would do Euclidean distance. I agree that there are other ways of going about it. And it may
Because function has done similarity of graphical communication networks with phase rank.
Yes.
And remarkably, and now we understand why, even when you don't have metrics, and you have something which we now call similarity or similarity measures, you actually get
absolutely. Yeah. So I agree that the classification on a given thing on what the closest one is this is not necessarily the best metric to go by.
Thank you.
Yeah, and this is still traffic data over the course of a single hour, so for each of these graphs?
So this is, the way I do this is I take every hour over the course of a year, and I'm going to use that as my data set to cluster. Right?
Okay.
And then this is the medoid. So this is just the centroid of all the data points that I clustered as being in that single mode.
Okay.
Many questions, but one important is how representative is median or mean calculations versus looking at extremes or air points or, like, I mean, do I care about the average or I care about the maximum?
Yeah, that's a really good question, and we went back and forth about this. I actually feel a lot more comfortable picking the median because the data is noisy, right? So I don't want to be swayed by the single flight that has a 6-hour delay.
So what about if I look at maximum minimum?
The range. The minimum is,
In my case, I
yeah.
have 14 hours, I don't care about the median. 14 hours.
That's true, but I guess what we were trying to back out here is what I'm interested in backing out is more systemic issues. So I would argue that this is the wrong method if I want to pick out maintenance errors, right? If I want to pick out system-wide, there is some weather impact that's affecting the airport, I would pick this. But you're absolutely right that this is not going to tell me the one-off maintenance.
Median is the correct metric with respect to size. Agree, because it's a robust size measure.
I'm trying not to get swayed by it's not going to tell me the
Okay.
worst thing that's happening here.
So if I understand this right, with these different graphs based on these delays, you have, let's call it different hubs. And so structurally, is there some finding there that certain airports, because I'm looking at the top right, there's an airport to the top right, in some others, like the one at the bottom left, it looks like O'Hare. So are there some sort of insights you have that these are the airports from this, from these graphs that are sort of the root cause of all the delays?
So, yes, and I'm not going to do it. So we've done some analysis, yes. So the kind of things where this becomes really interesting is I can be doing this for a time series over the course of a day, and I can look at what the characteristic types of days are. And when you do that kind of clustering, you start seeing that, and then I look at which airlines. Right? So depending on what type of data I have, the impact on different airlines is very different. Because the underlying reason why, because I'm only looking at delays and not the traffic, underlying traffic, I'm oblivious to why that connectivity is happening. But that connectivity is happening because there is some airline that is flying a lot between those 2 points that's causing that spread, right? So and that's where we're going more and more into looking at it as multi-layer networks, because we want to understand the airlines are interacting with the constraints that are happening at the hubs, but this is the how. The why goes back to the connectivity and the schedules and the demand. So absolutely, there's a whole set of questions there on why and also it's weird because you can see things like when do these things occur, right? And I can tell you already, this low-NAS state happens in the middle of the night. Like pretty much, you want to ask when are there no delays or they're overnight, right? So that kind of thing.
Question about for each of these data points, in other words, each of these hour-long observations of the entire network that you see, how many flights are there? I mean, it doesn't seem like there'd be that many flights on any given link, so.
Yeah. So, okay, I did, we actually filter, so I filter the data, underlying data, so that we only look at OD pairs that have at least 5 flights a day here. We've done 5 flights versus 10 flights, and the reason is then there are periods of time when there's more than one flight, right? Otherwise you're back to, you get completely thrown off by the one flight that was delayed. There's only one flight and it was 14 hours delayed, and you're thrown off. So we do some level of processing here, and then I show the validation. You'll see that I'm going to focus on the major airports and getting the delays right at the big airports. I want to make sure also that I'm getting the magnitude of the delays right at the big airports. That really matter.
So I have a question.
Yeah.
It seems like East Coast airports are more vulnerable than West Coast airports. I mean,
So-
is there a fundamental reason why that occurs? I mean, if somehow you could just magically make the Earth rotate the opposite direction, would the delay structure change?
Oh, you mean, yeah, but we had 9 a.m. after they had 9 a.m.? Possibly, yes. So there are reasons, I mean, you can ask, so I don't want, so one of the questions is, like I'm working with my student says, I think we should be looking at the network design problem here, right? So you know that the impacts happen here, what's the right airline network? And my point is, if you come back and say that, what United needs to do is to relocate its hub to Kalamazoo because it has the least delays. No, the East Coast airports have the most delay because there's a lot of demand, right? You have a lot more congestion. If you think about where the delays tend to happen, they're happening at the population centers because the demand is high because people want to be flying there. So I think, yeah, but it's...
But is it symmetric? I mean, lots of people want to go to LA.
That's true, but they have much better weather in California. I think it also has to do, so for example, there are things like the San Francisco delay states tends to happen in the morning. It tends to happen in the morning between May and October because they have fog every morning. So there are certainly temporal patterns, but I think, yeah, people want to fly into places that are congested, airports that are congested at periods of time when the weather is bad. I mean, we fly during Thanksgiving, and so I think I'm not sure that it's so fundamental as there isn't enough. I think it's less fundamental. It's just because, well, that's where the congestion is and that's where the demand is, and you don't get to build new runways in the middle of the East Coast. So you can't build a new airport, and if you do, there's not enough airspace, so you have congestion anyway. So I'm not sure it's more fundamental than that. At some level. Okay, so in any case, I can put all of this together and I can get a Markov nonlinear model. And one of the things that we can add is when you have these transitions, sometimes you actually have a sharp increase in delay. Because even though I assume that these transitions are random, if you think about what is triggering these transitions, it's things like there's a weather event that's going on, there's fog that onsets, so that leads to, there's some extraneous event that's actually triggering these transitions. So once I have this model, there's 2 things I'd like to do. One is I'd like to analyze it in some way. What can we say about this model? And the second aspect of it is going to be validation. Okay? So stability is, again, coming from controls systems background. Well, first thing you can ask is, I have this model, what can we say about stability? And the reason I'm interested in it, I think it's the first sanity check that we can ask, because stability really translates to, are delays likely to increase or decrease over the course of the day? And, well, I know that the system tends to reset overnight, so, they decay over the course of the day. Of course, I have these random transitions with a stochastic model, so I can talk about either mean stability or almost sure stability, and we've looked at both of these. I'm going to look at the case of almost sure stability, which is basically that I'd like to say that your system, if you keep repeating this, you're going to tend to zero. Your delays are all going to decay. You're going to tend to zero as time tends to infinity with probability 1, right? So you have these periodic transition matrices and they're going to go down. And what we can do is derive conditions for the stability of Markov jump linear systems with these time-varying transition matrices. But let's suppose I take a step back first and say, okay, I have these conditions. I'm going to say, assume a constant transition matrix and see what happens. So the fundamental thing in terms of, is every mode stable, or is, are some modes stable, unstable? We can ask that. So if you have a linear system, it's easy to check whether it's stable or not. You just look at the spectral radius of your state matrix, and if it's less than 1, you're going to be stable. If you're greater than 1, you're going to be unstable. This is just shown for the different modes, right? And we see that the ones which are decreasing delay modes are either stable or they're close to being stable, whereas the ones where the delays are increasing, as you'd expect, are unstable. But of course, John is not going to say, but the stability, if you have a switch system, the stability of a single mode is neither necessary nor sufficient for the stability of the switch system. Because you could be switching between unstable modes and being stable, you can switch between stable modes and become unstable. So while this is interesting, it's not telling us very much. So the next thing we can do is say, well, I know that I have these random transitions, so I'm going to look at the year of data, and I'm going to consider the average transition matrix for every hour of the day, and I'm going to use that and see whether the system is stable or not. Well, the system is not stable. But I know the system is stable because I know that delays decay overnight. So this is really, for us, the sanity check fails, and we realize, well, it's a failure of the model, because I assumed here that this is the probability. So this picture is telling me that at any hour of the day, the probability of my switching from, for example, the high NAS increasing mode to a high NAS decreasing mode is, somewhere around here. It's 0.5. But that really varies. That transition matrix itself varies by time of day, and I'm not ignoring that. So what do I mean by that? If I look at every hour and I find what the transition matrix is, we find that there are very strong temporal patterns here. So I'm just playing a movie which says every hour, what does my transition matrix look like? And we see that early in the day, we tend to transition to the increasing delay modes, and then later in the day, we're going to all transition back to the decreasing delay mode. So really, my model should be including these temporal variations. So when I do that, and we use the time-dependent transition matrices and then check our conditions, we realize that in fact the model is stable. So really, the earlier thing was not it was a failure not of the analysis, but of the model that we had. And the more key, like the insight here, which operationally you'd say, oh, yeah, but that makes sense, is the system really, the way it behaves is because of the temporal dynamics, right? The demand has temporal patterns, a lot of the disruptions in terms of the weather have temporal patterns, and so these temporal variations in these transitions are really critical for stabilizing the system. Which then, I think where we want to follow this on as engineers is, if I can actually schedule, if I know how to trigger those transitions, and I know they're what is stabilizing the system, then the performance thing is going to be how do I trigger the optimal transition in terms of modes.
Do you use Fourier theory or just the Pono theory for that?
This is just the Abnam theory.
Time, right?
Yeah, exactly. So this is just validation of that model. So what we do here is we learn this model using 2011 data. 2012, we can look at basically start off the initial condition and say how is the day going to progress, right? What is my prediction of how the day is going to progress based on that model. So the model really has 6 discrete modes, and then I'm splitting every mode into 2 depending on whether I think it's going to be increasing delay or decreasing delay. We see this is basically the total system delay, and total is defined as the top 35 airports. I'm looking at the total, adding the delays across those top 35 airports. And we see that we actually do, and the whiskers are the standard deviation of what we see. And we see that it is very uncertain, right? So there's a lot of things that can happen, but the red is the actual data and the blue is the model, and we actually do capture fairly well, even with the simplified model, the progression here. We are a little slow to catch on to when it transitions to the increasing delay states, and I think part of that is 6 modes is not enough to get everything that we need. And then we see that if you look at some of the major airports, we actually do mimic what is happening in practice reasonably well, even with this extremely simplified
Everything is correct. The standard deviation of your model is always larger than
Yeah.
the actual.
Yeah, and I think that's
Means
because
you are missing some
transitions.
positive phenomena in the actual.
And I know, but I think that's because the set of decreasing mode transition modes that we have is probably not enough to capture all the ways in which you can decrease, right? Because I'm constraining it to be, I can only have 6 decreasing modes. I think we need to increase that. But we're still, I mean, we're happy that we're getting the rates and things generally right with this fairly simple model, so which makes us happy. I did say that I was going to talk a little bit about those parameters, and I'm not going to go into a whole lot of detail. This is just telling me, the estimated alphas that I had between for every airport. The inbound delay persistence and the outbound delay persistence. We see that at most of the big major airports, those numbers are fairly high, which means that the queues take longer to dissipate and the delays tend to persist, whereas the less congested ones, you have larger numbers. These things do relate to scheduling that's happening within the airport and the airlines, so one of the things is how do you go and look at that. I'm not going to show the betas, but if you look at that, you sort of get this idea as to the relative, how much slack is being built into schedules for flights that are going between one airport and the other, so that you can allow these delays to take A versus good. Okay, where are we going with this? I think I talked about a few of these before. I mean, there are questions we can ask on how long do you tend to persist in a mode, which goes back to the dwell time of these systems. There are other notions of stability we can look at. So in more recent work, we started looking at maybe you want finite time stability. So I really want to show that I'm going to stay bounded fast, as opposed to I'm going to go to 0 eventually. So asymptotic stability may not be the best notion of stability to look here. I think, as I mentioned earlier, if we could establish causal relationships between traffic flow management initiatives, so things that are done in terms of the control and some of these mode transitions, that tells us something about, we can come up with optimal switching laws on what the right switching needs to be in order for us to decay as quickly as possible. So that's another thing that we're looking at. We've been looking at predicting future delays and delay states, and we've seen that looking at the sort of network delay state is actually very helpful in being able to predict future delays, and so that's a direction that we'd like to continue in as well. And then, as I mentioned earlier, really you have multiple airlines, you have cancellations, you have the operations themselves in terms of the traffic demand, and then you have the impacts. So one of the things that we're trying to do is to understand the interactions between these multiple networks. And then the other aspect, which I think is becoming more important in a lot of these systems, is interactions between different infrastructure networks. So in particular, looking at some of the taxi data from these different cities and interactions with airports. So the most recent example of this from a couple of years ago was in Atlanta, when there was a big snowstorm. You managed to clear out the runways in time, but then the streets are all closed, which means you can't get the pilots in. So, there's no point in opening up your airport if you can't actually get people to the airport. So then it becomes, if we can model the, so we've been looking at New York City taxi data, and we're seeing that there's a lot of this sort of time varying connectivity between inbound and outbound trips to the 3 airports in the New York area. So we're trying to understand what happens after a storm, for example, and that's all that. Okay. I'm trying to look at the time here. So I was going to talk about optimization. Maybe I'll talk at a really high level and then I'll
I'll ask all those questions so you never get to the
So,
We can take time.
okay, I'm going to hit some of the key points of this, and then I want to hit some of the bigger picture things. Okay, so one of the reasons why we're interested in what do we do about these delays and where do these delays occur, right, as opposed to the how, is this is the day, these are flight tracks into the New York area, these are storm cells that are moving into the New York, Philadelphia area. Red position of the aircraft, 5-minute history. And you see that as the storm moves in, you start having these holding patterns that go all the way to Iowa here, and then when the storm moves south, you have holding patterns that go all the way down. And part of the reason this happens is that there's not enough, well, you could argue that the reason this happens is there isn't enough predictive decision making that's happening where you know that the weather is going to move in here, so maybe you need to delay this. And a lot of the work that Mike's been doing over the past few years is how do you optimally design the ground delay program so that they're not burning fuel up here in the air, right? So that, but if you don't do that, this is what ends up happening. So if you think about the capacities that you're trying to allocate, there's two things that we care about when we're trying to manage this airspace. So one is the airport capacities themselves, and here there are trade-offs. And these trade-offs tend to occur based on what are known as capacity envelopes. So in any hour or 15-minute period, how many arrivals, how many landings can I have, and how many takeoffs can I have? If you use all your runway resources for one, you're not going to have very many of the other. And so you're going to have these capacity envelopes. But these envelopes are going to depend on the weather. So depending on whether it's good weather or bad weather, you can have a significant reduction in your capacity, so the envelopes can look very, very different. Okay? So, and that's going to be one aspect of the constraints. The other is on the airspace side, right, where the airspace itself is divided into smaller regions called sectors. I'm sorry you can't see the picture here. And these sectors depend on their shapes or the geometry, but they also depend on how many routes you have going through that, how these flows are oriented with each other, who the air traffic controller there is, so the workload of the air traffic controller, the weather, and so on. So you also have these airspace capacities. In the US, these tend to dominate. These aren't so bad except when there's bad weather. In Europe, these are actually pretty significant, where you tend to have scheduling to hit airspace slot times as much as you do at the airport. Now, if you think about optimizing this network under the centric things, there are two things that make the optimization hard. The first is what I talked about earlier, namely the incredible amount of connectivity that's there in the system. Right? So it turns out that only about 6% of the aircraft, the physical aircraft in the system, fly with just one flight a day. Most aircraft fly some, between 4 and 6 flights. So what this means is, if I say, look, the optimization problem is extremely hard and intractable. So what I'm going to do is to break it down into smaller chunks and solve, optimize 1 hour at a time. I got to be very careful doing that, because if I decide that it's optimal for me to cancel or to delay a flight by 3 hours, this hour, at 6 a.m. in the morning, if that flight is doing another 10 trips, I've implicitly delayed all 10 without realizing I'm doing it. So we have to be careful about it. The second is that the capacity forecast, well, I said your capacity depends on what your weather is like, but the weather is uncertain, so the capacity itself is likely to be uncertain, and so we need to be able to incorporate that as well. So this is basically the problem of air traffic flow management. Amedeo Odoni in the late 80s was the first person to come up with a mathematical formulation here, and the idea is, well, I can think about a deterministic version and a stochastic version. So the simplest deterministic version would be, I have a set of flights. I know which aircraft is scheduled to fly those flights. I know what the capacity is likely to be. I would like to find a plan for every single aircraft. I'd like to identify a trajectory, by which I mean I'd like to know when to take off, what route to fly, where, how fast I fly on different regions of airspace, when I come in and how I land, in order to optimize, maximize some benefit, right? Minimize some cost or maximize some benefit, or maximize the difference between how much revenue I'm getting and how much I'm spending, and so on. The stochastic case is going to be, I want to maximize the expected value of this, and I want to satisfy a bunch of constraints, but I want to do this irrespective of what scenario, what uncertainty is realized. The constraints that I have are those capacity constraints that I talked about earlier, both in the airspace and at the airports. I want to make sure that I take into account connectivity between flights and the minimum turn time. You need some minimum amount of time for people to get off a plane and new people to get on the plane. And then there's physics, which is I can't go infinitely fast, and there's some limited amount of fuel, so I have maximum and minimum transit speeds that I have. And then you can ask, what are my variables? What can I control? And there's not a whole lot you can do, right? You can hold them in the ground. That's the cheapest, safest option. You can hold them in the air. It's more expensive, and people are a little more wary about doing that. You can give them a different route, and then which is a little more expensive because it's more airborne delay, but also more coordination, and you can cancel it, which means you've pretty much given an infinite amount of delay, right? So you stack the whole thing. So ultimately, what we have is, the way we're going to model this is we're going to come up with a trajectory. The trajectory is going to assume that time is discretized, and I'll talk later about some experiments with 1-minute intervals, but let's suppose we're discretizing time into 5-minute intervals. My trajectory is going to be tell every aircraft, leave here at this time, maybe I spend some time on the ground, when to get to the runway, when to get to the first fix or point in the airspace for departure, when to enter each of these sectors, so this route through these, so times at each of these nodes, and then when to come in and land, and then the next flight for that aircraft and so on, right? And those times are going to be discretized in whatever discretization I pick. The uncertain version of this is going to be that I don't know exactly what the capacities are going to be. I have a scenario tree which says that this is what the weather is going to look like everywhere, but with some 40% probability at 9:30 this is going to happen, with 60% probability something else is going to happen, and then at 10:45 I have a different set of things that can happen and so on. So here, when you think about giving a plan, you have to say, well, you can leave the gate at this time, you reach this gate, this fix at the runway at this time, but if scenario 1 happens, do this, if scenario 2 happens, do that, and so on. And the important thing here in the optimization is going to be that you can't say at this time, make a decision based on whether it's scenario 5 or scenario 6, because I can't distinguish between those two till 11:15 in the morning, so you can't tell me do one if it's scenario 5 and something else if it's scenario 6 at 9:30 in the morning, because I don't know which of those is going to happen, right? So that's going to be the whole idea. So what are we going to do? I'm not going to go through the full formulation. The idea is going to be maximize the some objective function, the benefit of all the trajectories that we pick for every aircraft, subject to these constraints, which is every aircraft can only be doing one thing, right? So it tells you all the things that the trajectory for the flight. You've got to satisfy the sector capacity constraints, the airport capacity envelope constraints, and then you have a binary variable that says, am I going to pick this trajectory or not? This is going to be a large-scale optimization problem, and maybe we can. I'm happy to talk about how we solve this and everything else offline, but I think you realize I'm way out of time. So the idea is going to be basically that we're going to solve this, and the big difference in what we've done compared to the approach that's been taken before is we use column generation to solve this. For the more controlled optimizations, people dual decomposition to solve this. And the idea is going to be that each subproblem that you have is going to be for a given aircraft, right? So I'm going to solve the subproblems independently for every airframe, saying, here's what you need to do, here are the times, here's the flights that you're operating, and so on. But the nice thing is those subproblems you can formulate as the longest problem, and you can efficiently solve using programming. And we can implement this parallelly. And then we have some heuristics to basically assess, to get bounds and also assess the optimality gap so that you know when to stop. So just in terms of a high-level schematic on how this would go, you start with the initial schedules or the initial plans that the airlines would like to have scheduled to fly, the capacity forecast that you have, and the operational constraints. So this is the deterministic version. You check the feasibility, and then depending on the demand on every one of your resources, you're generating a set of prices, you're sending the prices to the subproblems, and the nice thing about these subproblems is since they're decomposed by every.
You got it, yeah.
Okay, sorry?
You got it.
Dual pair.
That's why you have price.
Exactly, yeah, that's a goal, right? And the nice thing about this is every airline can solve this internally, right? So I know how much those prices are for those resources. I can decide that I can fly a different route for one of my aircraft and do better, and then you come back with new trajectories and new
Do you have
valuations.
any results or estimates as far as when you relapse in the program?
So we do,
Any
yeah.
particular structure of the network to allow you to say that the tax solution is close to the optimal?
So we basically, one is experimental and the other is that we basically have bounds, right? So we keep checking and we terminate this when you're within 0.1% of the optimum.
Thank you.
Or you can't add anything. So there's two conditions, but yeah, pretty much those are heuristics. We can't say something about this. This is known to be hard, so we're not going to. The LP relaxation is not going to be integer optimal. But what this allows us to do is basically solve really large problems in very realistic time. So for the deterministic version, what we end up with is we can solve at a 5-minute discretization. This was on a MacBook Pro. We can solve days, so it has 8 virtual Pro cores, and 24-hour time you can solve in about 5 minutes. The stochastic version is takes a little longer, but it depends on the number of scenarios and so on, and you can come up with good results there.
What is ATEM?
Air traffic flow management, sorry. That original problem that I talked about, it's jargon. Now, what I wanted to show, so then we can do this and we can solve, optimization for sort of 5 examples. This is about 70,000 flights with sector capacity constraints from today. I wanted to end with some work that we've been doing more recently as part of our NASA SDIR, where we're looking at future demand sets and also looking at parallelizing on the cloud, right. So here, we also want to introduce unmanned demand. So this is from the FAA's JPDO demand set, and we have manned as well as unmanned traffic. We have about 40,000 flights with 25,000 unique airframes in this data set, telling us what is each of those aircraft is scheduled to fly. We have some estimates of what the sector capacities and the airport capacities are likely to be, but we also have unmanned demand in this data set. And so there's about 35,000 flights. The unmanned demand is a little different because a lot of it is fish spotting and agricultural missions, which means that they're not looking for the shortest path between A and B. They actually want to spend 2 hours going round and round, so you want to make sure that you do it. They're also at a wide range of altitudes, so the guys who are very low, we're going to just route as they want. The guys who are in the same altitude as commercial traffic, we're going to be optimizing with them. Right? So, and this, what we have is, it's a single instance on EC2 on Amazon Web Services. There's 40 cores and there's 77,000 flights. So the red aircraft is going to show up in a minute, hopefully. Something happening? Yeah. Okay, it's going to start. You'll see it soon. So the red aircraft are the unmanned aircraft, and the blue aircraft are the manned aircraft in this. See, there's a lot of red, right, because they are actually fairly aggressive in their estimates of the unmanned traffic demand. You can see those fish spotting missions out here off the Atlantic.
So the red are the low and the high?
Not necessarily low. So they're all the way up to in a range. So some of them are, there's a small, there's reasonably small. So the thing is, a lot of the surveillance ones are actually at reasonably high altitudes as well. So they're getting up there. And here what we are doing is the trajectory fidelity we have at a minute, the airspace constraints, the airport and the airspace constraints are at a 5-minute resolution. And we can solve, we can do this with 8-hour chunks in less than a minute, but you can do the full 24 hours in less than 5 minutes. Okay, so I'm going to skip this. But I'm going to end with where I think some of this is going, and I think really this is a picture of New York Times headline. Robot piloted plane makes safe crossing of Atlantic. So the question for you guys is, when do we think this is a headline from?
Looks old.
It looks old, it's good. Yeah, I'm really good at Photoshop though. So this is from September 1947. So we've known how to fly one aircraft remotely piloted for almost 70 years. We still don't know how to integrate it into the rest of the system. So that's really the integration, the systems challenge is what remains, right? I also love this quote in that because it not only said we were going to have drone warfare, but it also said Amazon Prime was coming, so it's going to be cargo, right? But
there's no mystery that it went from Newfoundland to Oxford.
Canadians.
Competition for traffic over that.
That's true, and also the remarkable thing is there were 14 people on board that plane, including 9 members of the press.
Really?
That says something, right? We should try to start getting people to do that more. But really, I think that level of autonomy, the integration of autonomy into what we have is what, the remaining challenge here, right? The next part is, of course, with the resource allocation itself. I think with the human factors, the stakeholders, we do need to be looking at things like fairness, and especially when you have these multiple network resources, we do everything first come, first served today, which works fine. Well, it works adequately when you have one resource, but you can't be doing that in a network of resources and enforcing first come, first served everywhere. And then there are questions of what are the incentives, especially when you think about stochastic optimization and the privacy, which is going to become important in a lot of these things, especially when you have unmanned systems. Same thing with security. I think Netherlands has done a lot of work in this area, but again, if you're going to be using this information to make decisions and to do routing, then you do need to be thinking about the security of these systems, either because there's error or malice, right? So both of those are equally important. And I think in the long term, there's questions of interactions, and these interactions are between different infrastructures, like I talked about earlier, between humans and autonomous systems and vice versa, and automation, and also between things that we do in terms of resource allocation, months ahead or hours ahead, and the things that we do at a very tactical level in terms of controls. So I'm going to stop there. There's a bunch of other things that we worked on, including trying to model objective functions of air traffic controllers that I won't talk about. But I think ultimately we are in a place where we have the ability and the opportunity to make a difference. So I think it's a great area of research.